Greetings, cosmic explorers. My name is Ben-Emmett, and today we're embarking on a journey to the very edge of time and space. For decades, we've looked up at the stars armed with ever-improving tools, each one peeling back another layer of the cosmic onion. But nothing, and I mean nothing, has prepared us for what we're seeing now. We have a new eye in the sky, a golden hexagonal marvel of engineering called the James Webb Space Telescope. It's not just an upgrade, it's a revolution. It's humanity's most powerful, most sensitive, most ambitious eye on the cosmos, and it's staring deep into the past. The light from distant objects takes time to reach us, so when we look far away, we're also looking back in time. JWST was designed to see the very first glimmers of light after the Big Bang, the cosmic dawn, when the first stars and galaxies ignited. We had theories, we had models, we had educated guesses about what we'd find. But the universe, as it so often does, had a few surprises in store for us. The initial data pouring back from JWST isn't just adding footnotes to our textbooks, it's forcing us to rip out entire chapters and start again. What we're seeing is challenging the very foundations of our understanding of cosmic origins and evolution. The universe appears to have gotten a much earlier start on building complex structures than we ever thought possible. It's like arriving at a party you thought was just getting started, only to find it's already in full swing. So buckle up. We're about to explore the 10 most mind-blowing discoveries from JWST that are rewriting the story of everything. This isn't just astronomy, this is our cosmic origin story, unfolding before our very eyes. Let's start at the beginning, or what we thought was closer to the beginning. The Big Bang happened about 13.8 billion years ago, a moment of unimaginable energy and density. For a few 100,000 years, the universe was a hot, opaque soup of particles. Then it cooled, atoms formed, and the cosmos became transparent. This is when the cosmic dark ages began. We've always asked, when did the first lights turn on? When did the first stars coalesce into the first galaxies? Our model suggested a gradual, slow process, taking maybe 500 or 600 million years. JWST was built to find those first galaxies, and boy, did it deliver. It peered into the blackness, using its infrared vision to capture the faint, red-shifted light that has been traveling across the universe for nearly its entire existence. And there they were, not just a few faint smudges, but multiple candidates for galaxies that existed a mere 280 to 400 million years after the Big Bang. Think about that. If the universe's history were a single year, this is like something happening in the first week of January. One of these ancient stellar cities has been nicknamed Moam Z14, which stands for Maisie's galaxy at redshift 14. The redshift number is a cosmic yardstick. The higher the number, the farther away and further back in time the object is. A redshift of 14 is simply staggering. It pushes the frontier of observation right up to the edge of what we thought was possible. These aren't just dots of light, they are collections of stars, gas and dust, organized structures in an infant universe. Finding them was one thing, but their very existence poses a profound puzzle. How did they get so big, so fast? The standard model of cosmology, the Lambda CDM model, describes a bottom-up formation. Small things like star clusters and dwarf galaxies form first and then merge over billions of years to create larger galaxies like our own Milky Way. It's a slow and steady wins the race kind of model. It's elegant, it's well supported by evidence, or it was These early galaxies are like finding a fully grown oak tree just a month after you planted the acorn. They are far more massive and developed than our models would predict for that era. It suggests that the process of galaxy formation was perhaps more efficient, more explosive, or followed a different path altogether in the early universe. We're not just looking at a picture, we're looking at a piece of evidence that tells us our story of cosmic creation needs a serious rewrite. This discovery forces us to reconsider the fundamental ingredients of the early universe. Did the first stars, the so-called population 3 stars, pure hydrogen and helium giants, form and die much faster, seeding the cosmos with heavy elements quicker than we thought? Or could there be another mechanism at play, something involving dark matter, halos, or primordial black holes that accelerated the whole process? JWST hasn't just given us an answer, it has given us a dozen new, more profound questions. And in science, that's where the real fun begins. If the galaxies at redshift 14 were a surprise, then what JWST found next was, for some astronomers, a cosmic miracle. And that's not a term scientists throw around lightly. While looking at the early universe, specifically at a time about 700 million years after the Big Bang, the telescope spotted something that, according to our prevailing theories, simply shouldn't be there. It was a galaxy, but not just any galaxy. It looked mature. It looked old. This galaxy, cataloged as ZF-UDS 7329, had a stellar population that appeared to be about 1.5 billion years old. Now wait a minute, how can a galaxy contain stars that are 1.5 billion years old when the universe itself was only 700 million years old at the time we're observing it? That's like finding a 40-year-old person in a world that's only 20 years old. It sounds impossible, a paradox that strikes at the heart of our cosmic timeline. What this implies is that this galaxy must have formed its stars incredibly early, perhaps just 200 or 300 million years after the Big Bang. And then for some reason, it just stopped. It became what astronomers call a quenched or passive galaxy, no longer actively forming new stars. It just sat there, its stellar population aging until its ancient light began its long journey to JWST's mirrors. This is a galactic life cycle we typically see much later in cosmic history. This discovery is a direct challenge to our understanding of galactic evolution. We thought galaxies in the early universe were all bustling, chaotic, star-forming factories. The idea of a large, sedate, retired galaxy in such a youthful cosmos was unheard of. It suggests that the mechanisms that shut down star formation, a process we're still trying to fully understand in modern galaxies, were already operating with shocking efficiency at the dawn of time. So why is it a cosmic miracle? Because its existence stretches our models of cosmology to their breaking point. To form such a massive collection of stars so early and then have it all shut down requires a series of events that are, under current theories, exceptionally rare, if not impossible. It's a statistical improbability, an outlier of such magnitude that it makes you question the whole data set. It is a beautiful cosmic anomaly. This single object forces us to ask some hard questions. Are our methods for dating stellar populations wrong when applied to the early universe? Or did this galaxy form through a completely different, hyper-efficient process we haven't even conceived of yet? Perhaps involving the direct collapse of enormous gas clouds? Whatever the answer, ZF-UDS 7329 stands as a testament to the fact that the universe is more creative and more surprising than our simulations had ever allowed us to imagine. We all have a certain cosmic vanity, don't we? We look out into the universe and we search for things that look like us, like home. We see faces in the clouds, canals on Mars, and we search for Earth-like planets. So it's no surprise that we're fascinated by our own galaxy, the Milky Way. It's a beautiful, grand design spiral galaxy, a swirling pinwheel of 100 billion stars. We thought it took billions of years of cosmic evolution, of mergers and graceful gravitational dances to create something so elegant. We assumed that the early universe was a messy place filled with clumpy, irregular, train-wreck galaxies. The beautiful spirals, we thought, came much later, once things had time to settle down. Once again, JWST looked at our assumptions and said, "Hold my beer," because it found Xulong, a galaxy that looks remarkably like our own Milky Way, complete with a distinct bar of stars at its center and emerging spiral arms, a cosmic twin. The astonishing part is when it existed. JWST saw this galaxy as it was just 1 billion years after the Big Bang. That's incredibly early to see such a well-ordered, structured galaxy. Finding a barred spiral like Xulong so early in cosmic history is like finding a perfectly preserved Roman villa while excavating a Stone Age settlement. It's an artifact that seems to belong to a much later, more developed era. The name Xulong is fitting. It comes from Chinese mythology and refers to a torch dragon that created day and night by opening and closing its eyes, illuminating the darkness. And this galaxy is certainly illuminating the dark corners of our knowledge. The presence of a stellar bar is particularly significant. These bars are thought to be powerful engines of galactic evolution. They act like cosmic traffic directors, funneling gas and dust towards the galactic center. This funnel in action can trigger bursts of star formation and critically feed the supermassive black hole lurking at the galaxy's heart. The fact that such a mechanism was in place so early suggests that the evolutionary track for galaxies, like the Milky Way, was established much sooner than we thought. It means the universe wasn't just building massive galaxies, it was building complex galaxies with internal dynamics that would shape their future for billions of years. Xulong isn't just a pretty picture, it's a snapshot of our own galaxy's potential childhood. It provides a direct observational link between the chaotic early universe and the grand spirals we see today. It tells us that the path to becoming a Milky Way might be shorter and more direct than we ever imagined. It's a humbling and exhilarating thought that across the vast expanse of time, we can see a reflection of ourselves, a galactic sibling born in the cradle of the cosmos. The universe is a violent place. Stars explode, galaxies collide, and some of the most energetic events imaginable are the mergers of black holes. When two of these gravitational behemoths spiral into each other, they release more energy in just a few milliseconds than all the stars in the universe combined. This energy ripples outwards through the fabric of space-time itself as gravitational waves. We've detected these waves here on Earth with instruments like LIGO, but seeing the light from the aftermath of such a merger, well, that's a different challenge entirely, especially if it happened in the distant past. Yet again, this is where JWST excels. It detected the signature of two supermassive black holes in the process of merging. This wasn't just any merger. It was the most distant and therefore the earliest black hole merger ever observed, taking place when the universe was only 740 million years old. The system, known as ZS7, was initially identified as a peculiar-looking galaxy, But when JWST's spectrographs dissected its light, they found the telltale signs of a cosmic cataclysm. They saw extremely dense gas, rapid movements, and energetic signatures that could only be explained by not one, but two monstrous black holes circling each other in a final doomed dance before becoming one. One black hole was estimated to be 50 million times the mass of our Sun. The other was likely of a similar mass. This is, simply put, mind-boggling. We are still grappling with how supermassive black holes get so big in the first place. The leading theory is that they grow over billions of years, steadily feeding on gas and stars, and occasionally merging with other black holes. But this discovery shows two already massive black holes on the verge of merging in an era when we thought they should still be in their infancy. It's like finding two adult blue whales in a pond where you expected to find tadpoles. This observation provides a crucial piece of evidence. It suggests that mergers must be a primary way that black holes grow, even in the very early universe. It supports the idea that the seeds of black holes must have been very large to begin with, or that the process of accretion and merging is far more rapid and efficient than our models accounted for. It's a smoking gun for the theory of hierarchical growth, but on a timescale that is frankly terrifyingly short. Imagine the scene. In a universe still finding its feet, two of the most powerful objects in existence are locked in a gravitational struggle. The space around them is warped, light is bent, and a storm of high-energy radiation is unleashed. And 13 billion years later, a telescope built by curious apes on a small blue planet captures the faint echo of that titanic collision. It's a reminder that the cosmic story is written in violence and creation, and we are just now learning to read its earliest chapters. For a long time, we thought of the supermassive black hole at the center of our own galaxy, Sagittarius A, as a gentle giant, a sleeping monster. At 4 million times the mass of our Sun, it's certainly a behemoth, but observations suggested it was relatively quiet, only occasionally snacking on a bit of gas or an unlucky star. It was the quiescent supermassive black hole next door, a perfect laboratory for study, precisely because it wasn't doing much. JWST, with its unprecedented infrared sensitivity, decided to take a closer look. It peered through the dense clouds of dust and gas that obscure the galactic center from view in visible light, and it found that our neighborhood monster is not so sleepy after all. In fact, Sagittarius A is far more active and unpredictable than we ever gave it credit for. It's a flickering, flaring, restless heart at the center of the Milky Way. The telescope captured images of the hot gas swirling in the accretion disk, right at the edge of the black hole's event horizon, the point of no return. These images, taken just hours apart, showed dramatic changes in brightness and structure. It was like watching the weather patterns on a cosmic scale, but with storms powered by gravity so intense it warps space-time itself. These flares are the result of magnetic interactions in the superheated plasma, a process we are only just beginning to model. This variability is crucial. It tells us that the immediate environment around Sagittarius A is a dynamic and chaotic place. It's not a steady trickle of gas, but a lumpy, turbulent flow. These observations allow us to test Einstein's theory of general relativity in the most extreme environment in our galaxy. How does matter behave when it's being stretched, heated, and accelerated to near the speed of light by a black hole? JWST is giving us the raw data to answer that. Furthermore, these findings have implications for our understanding of how all galaxies work. The activity of a central black hole can have a profound impact on its host galaxy, a process called feedback. Flares and jets from the black hole can blow gas out of the galactic center, regulating or even shutting down star formation. Seeing this process happen in real time, even on a small scale, in our own backyard gives us a vital insight into this cosmic balancing act. So the next time you look up at the night sky towards the constellation Sagittarius, remember what's hidden there. It's not a sleeping giant, it's a dynamic, flickering engine, a place of extreme physics and unpredictable power. JWST has pulled back the curtain, revealing that the heart of our own galaxy is a much wilder and more interesting place than we ever knew. It's a little unsettling, but it's also fantastically exciting. We've been talking about how supermassive black holes grow. The standard picture involves a star-mass black hole born from the collapse of a massive star, which then slowly feeds and merges its way up to millions or billions of solar masses. This is the seed theory. But as we've seen, the discovery of huge black holes in the very early universe puts a lot of strain on this model. It's just too slow. So, what if there's another way? What if you could skip the awkward teenage phase and be born a giant? This is the idea behind direct collapse black holes. The theory goes like this. In the early universe, under very specific conditions, a truly colossal cloud of primordial gas, hundreds of thousands of times the mass of the sun, could become unstable and collapse all at once, not into a star or a cluster of stars, but directly into a massive black hole. No supernova, no stellar remnant, just a direct plunge into a singularity. It's a cosmic shortcut to creating a monster. For years, this was just a compelling theory, a potential solution to the timing problem, but with no direct evidence. Finding such an object would be like finding a fossil of a completely unknown branch of the evolutionary tree. JWST, however, may have found one. In a galaxy called UHZ1, observed when the universe was just 470 million years old, it found a black hole that was astoundingly oversized for its host galaxy. It was a giant head on a tiny body. The black hole in UHZ1 is estimated to be tens of millions of solar masses, comparable in mass to all the stars in its entire galaxy combined. In a normal galaxy, the central black hole is typically only about 0.1% of the stellar mass. This one was close to 100%. This extreme ratio is very difficult to explain with the standard seed and growth model. It just doesn't have time to get that big. While its host galaxy is still so small, the properties of this object, however, match the predictions for a direct collapse black hole almost perfectly. The intense radiation signature, the mass, and the age are all consistent with the idea that we are looking at a black hole that was born big. It didn't grow from a stellar seed, it was born from the monolithic collapse of a primordial gas cloud, a true heavyweight from birth. If confirmed, this is a monumental discovery. It would provide the first real evidence for a second channel of supermassive black hole formation, a channel that could explain the presence of the quasars and massive black holes we see lighting up the early universe. It would mean the cosmic zoo contains at least two different species of these gravitational monsters. The universe, it seems, has more than one recipe for cooking up a black hole. You know, the universe isn't empty. The space between galaxies, what we call the intracluster medium, is actually filled with a thin, superheated gas. So, what happens when a galaxy moves through this medium at high speed, like say a few million miles per hour? Well, it's kind of like what happens when a swimmer dives into a pool. There's pressure, a resistance, For a galaxy, we call this ram pressure, and honestly, it can be strong enough to strip the galaxy of its own gas and dust, the very stuff it needs to form new stars. This whole process, called ram pressure stripping, creates some of the most beautiful and honestly ghostly structures we see in the cosmos. As the galaxy plows through the intercluster medium, its gas gets pushed back and trails behind it, often forming these long, delicate tentacles of star-forming material. These spectacular objects have been nicknamed jellyfish galaxies, and they really give us a stunning real-time look at galactic interaction and evolution. Just recently, JWST turned its powerful gaze to one of these galaxies, JO206, which is about 700 million light-years away in the constellation Aquarius. Now, Hubble had seen this jellyfish before, but JWST's infrared vision let it peer right through the dust and see the intricate details of the stripping process with unprecedented clarity. It was honestly like switching from a standard X-ray to a high-resolution MRI. The telescope could map out the structure of those trailing tentacles with incredible precision. It could even distinguish between the older established stars in the galaxy's main disk and the brand new infant stars being born inside those stripped gas trails far away from the protection of their parent galaxy. This is star formation happening in a truly bizarre and hostile environment, triggered by the very process that's, well, slowly killing the galaxy itself. By studying the dust in these tentacles, JWST could also figure out how the stripping process works over time. It saw that the dust grains in the tentacles were actually smaller than in the galactic disk, which suggests that the harsh environment of the intercluster medium was eroding them, or maybe the stripping process itself was selective. These are the kinds of subtle clues that help us build a complete physical model of how galaxies live and die within galaxy clusters. The story of the jellyfish galaxy is, in a way, a dramatic tale of cosmic struggle. It's a galaxy fighting a losing battle against its environment, its lifeblood being siphoned away into space. But even in this slow death, there's a final, beautiful burst of creation as new stars are born in its wake. JWST's observations of JO206 really give us a front row seat to this process, revealing the complex, violent, and honestly, surprisingly beautiful ways that galaxies evolve. Stars are, the engines of cosmic creation. They forge heavy elements in their cores, and when they die, they scatter these elements into space, providing the raw materials for new stars, new planets, and eventually for us. Understanding where and how stars are born is, honestly, fundamental to understanding our own origins. We call these regions stellar nurseries, which are vast clouds of gas and dust where gravity is slowly winning its battle against pressure and temperature. For years, we've studied these nurseries, but much of the action is hidden from view, shrouded by the very dust that fuels the star formation. Visible light just can't penetrate it, but infrared light, which is what JWST sees, can. The telescope has given us the ability to peer deep inside these cosmic clouds and witness the birth of stars with breathtaking clarity. It's, like having ultrasound for the cosmos. One of the most iconic images released by JWST is of the cosmic cliffs in the Carina Nebula. This is a region of intense star formation, where a wall of gas and dust is being carved away by the fierce radiation from massive young stars located just outside the frame. The image reveals hundreds of previously hidden stars and countless stellar jets and outflows, which are beams of material shot out by protostars as they accrete matter. Every point of light in these images tells a story. We can see the cocoons of dust where protostars are still forming, the shock waves where their powerful jets slam into the surrounding gas, and the way the entire cloud is being shaped and compressed by the stellar winds of its most massive newborns. This isn't a static picture, it's a snapshot of a dynamic, violent, and incredibly complex ecosystem. These observations are not just pretty, they provide hard data that allows us to refine our theories of star formation. We can measure the mass of the forming stars, the speed of their outflows, and the chemical composition of the gas they are born from. This helps us answer key questions. Why do some clouds form massive stars while others form smaller ones like our sun? How does the formation of one generation of stars trigger or inhibit the formation of the next? By studying these regions, we are essentially watching galactic evolution in microcosm. The stars born here will live out their lives, and their deaths will enrich the nebula with new elements, setting the stage for the next round of creation. JWST is allowing us to see this entire cycle with a level of detail that was honestly previously science fiction. It's a direct look into the cosmic factory that builds the worlds and suns of the future. For most of human history, the only planets we knew were the ones in our own solar system. In the last few decades, we've discovered thousands of planets orbiting other stars, which we call exoplanets. But the vast majority of these have been discovered indirectly by observing the subtle wobble of a star as a planet tugs on it, or the tiny dip in a star's light as a planet passes in front of it. Actually taking a picture of an exoplanet, directly imaging it, is, well, incredibly difficult. Though the problem is the stars are blindingly bright and their planets are fantastically faint. It's like trying to spot a firefly next to a searchlight from miles away. It requires blocking out the star's light with exquisite precision using a device called a coronagraph. JWST is equipped with state-of-the-art coronagraphs, and it has already put them to spectacular use, capturing a direct image of a planet named HIP 65426b. Now, this isn't the first exoplanet ever to be directly imaged, but it is a significant milestone for JWST. It was a test, a proof of concept to show that the telescope systems could perform this incredibly challenging task. And it passed with flying colors. The image it produced across several different infrared wavelengths was a clear and unambiguous detection of a world orbiting another star. What's particularly noteworthy about this observation is the mass of the planet. HIP 65426b is a gas giant about 6 to 12 times the mass of Jupiter. But in a more recent observation, JWST managed to directly image an even more elusive target, a planet with a mass similar to Saturn. This is the lightest exoplanet ever to be directly imaged. This is a huge step forward, pushing the technology closer to the ultimate goal of imaging smaller, rocky, Earth-like worlds. Why is direct imaging so important? Because it allows us to do something transit methods can't: study the planet's light directly. By breaking down the faint light from the planet into a spectrum, we can learn about the chemical composition of its atmosphere, its temperature, and even the presence of clouds. Each image across different infrared filters gives us another piece of the puzzle about what these distant worlds are actually like. This is the dawn of a new era in exoplanet science. We are moving from simply cataloging planets to characterizing them. JWST is not just a planet hunter, it's a planet analyst. Each direct image is a stepping stone, refining our techniques and pushing the limits of what we can see. We are no longer just inferring the existence of other worlds. We are beginning to see them, to study them, and to understand their place in the cosmic menagerie. While JWST's gaze is often fixed on the most distant reaches of the universe, it's also a powerful tool for exploring our own cosmic neighborhood. Its incredible sensitivity allows us to study the objects in our solar system with a fresh perspective, revealing details we've never seen before. From the atmospheres of gas giants to the surfaces of icy moons, JWST is providing a new family portrait of our solar system. Recently, the telescope turned its attention to a young star system, not unlike our own solar system in its infancy. There, in the cold inner region of the protoplanetary disk, where rocky planets are likely forming, JWST made a landmark detection frozen water ice. This is the first time we've detected water ice in the terrestrial planet-forming zone of a disk this cold. It's a crucial discovery, as it suggests that the building blocks of life, or at least a key ingredient like water, are available from the very beginning. This finding supports the idea that water-rich asteroids could be common in young solar systems, delivering water to nascent, dry, rocky planets just as they likely did for early Earth. It's a tantalizing clue that the conditions that led to life on our planet might not be so rare after all. We are seeing the raw materials for habitable worlds being delivered right where they're needed. Closer to home, JWST has been giving us spectacular weather reports from Saturn's largest moon, Titan. This is a world shrouded in a thick, nitrogen-rich atmosphere with rivers, lakes, and seas of liquid methane and ethane. It's one of the most intriguing places to search for exotic forms of life. Using its infrared instruments, JWST was able to peer through the haze and monitor Titan's weather. The telescope captured images of bright clouds bubbling up in Titan's northern hemisphere. By tracking these clouds over a few days, in collaboration with ground-based observatories, scientists could confirm that they were moving and changing shape, consistent with models of Titan's seasonal weather patterns. It was honestly like watching a storm front move across a distant alien world. These observations of both the very young and the much closer are two sides of the same coin. They are about understanding the conditions that create and sustain worlds. Whether it's detecting the ingredients for life in a system hundreds of light years away, or watching the clouds drift over a moon in our own backyard, JWST is connecting the dots. It's showing us the vast interconnected story of how planetary systems form, evolve, and maybe, just maybe, come to life. So, what does this all mean? We've journeyed to the edge of time, witnessed the birth and death of galaxies, peeked into the heart of a black hole, and watched clouds drift on an alien moon. Each of these discoveries on its own would be a landmark achievement, but taken together, they represent something more. They represent a fundamental shift in our cosmic perspective. The James Webb Space Telescope is not just collecting data, it's weaving a new tapestry of the cosmos, one with threads and colors we never knew existed. The universe, it turns out, is more complex, more dynamic, and God started with its grand projects much earlier than we ever dared to imagine. This is a profound moment for science and for humanity. We are living in an era when the answers to some of our oldest questions, where did we come from, how did the universe begin, are being rewritten in real time. The pace of discovery is honestly staggering, and it's inspiring a new generation of scientists, engineers, and dreamers. These images and data points are more than just science. They are a source of wonder, a reminder of the scale and beauty of the universe we are a small part of. They connect us to the cosmos in a deep and meaningful way. And the most exciting part, we are just getting started. The James Webb Space Telescope has been operating for a relatively short time. Its mission is planned to last for years, even decades. The discoveries we've talked about today are just the opening act of what promises to be an incredible scientific revolution. So, keep looking up, stay curious. Join us as we continue to follow the revelations from humanity's golden eye on the sky. The universe has more stories to tell, and we'll be here to share them with you. Thank you for watching.